Hi, I'm Ahmed. Here in Palo Alto at the Queen's Micro Summit series, we heard from leading Queen's researchers who are driving innovation and delve deep into the possibilities of tomorrow. During a fireside chat with Queen's researchers, alumni, and students. With that, let's get started.
Good evening. Good evening. First of all, I want to thank you all for coming here this evening. My name is Kim Fennell. I'm going to be your host for this evening, which means I'm not really going to say anything of much value. The two guys speaking after me are the ones you're going to want to listen to. But what I do want to do, first of all, in a true Queen's fashion, we're going to do a land acknowledgement. So work with me on that one. And so, first of all, we want to acknowledge that we weren't here first, and that the land we're located on is traditional territory of the Tamiya Nation, Ramaytush Ohlone, and Mawakma Ohlone peoples. So that being done, let me formally welcome you to the Queen's Micro Summit series. Now there's going to be 4 of these that Queen's is doing. This is the first one. This is the maiden voyage, so you get to see all the rough spots still being worked out as we do that. The next ones are going to be in Toronto, Vancouver, and Calgary. And the purpose at a high level is to kind of take you to the future as imagined by our Queen's researchers, and candidly also enabled by Queen's donors, some like you in the room, and we appreciate that very much. This is a new program that Queen's has been doing, these micro summits. They're designed to be small, as you can see, intimate. We want to give people a chance to get kind of immerse themselves in the topics, be able to ask some questions, and kind of give you exclusive access to the ideas, innovations, and visions for the future that our researchers are going to talk to you about. Before I go much further, though, I'd want to give a shout out to the Dean, the Queen's Dean of Smith Engineering, Kevin DeLuzio. Where are you, Kevin? All right. Thank you for being with us tonight and tomorrow night. We appreciate your support for this program and for being here. Now, this first summit that we're going to be doing, this one is focused on the future of computing, how computing will change in the future, but also how computing will change the future. And we've got 2 amazing researchers that are going to come up and talk about that in a moment. But first, since it's kind of a cozy little group, I thought we'd kind of get to know each other a little bit more. They've asked me to do a quick introduction on me. I said it's not really that important. But anyway, as I said, Kim Fennell. Arts and Science 79. I know you're doing the math right now and saying, damn, that guy is old. Truth be told, I was actually 1 credit short. They said if I came and emceed, I would get my diploma in the end. So that's why I'm here this evening. But no, seriously, I'm a very proud Queensman. I had a grandfather that went to Queen's, an uncle, a brother, a niece, and I'm proud to be on the Dean's Arts and Science Advisory Board. My own background is I am from Toronto, but I've been down here since '97. I was fortunate to run 3 different companies here, sold the last one to Uber. Spent 5 crazy years at Uber. If you ever want to hear crazy Uber stories, we could do that in the bar later on. That was between 2015 and 2020. And then for the last 5 years, I went to the dark side, and I'm now a venture capitalist. Anyway, one of the things that excites me, and I'm sure you guys as well, if you're down here in the Valley, is the whole concept of change and how technology can enable that change. And God, I hate when I say this, in 45 years, seeing the trends in this valley, one thing I can tell you is that the trends are interesting. Some of them rhyme, some of them repeat themselves, but what is undeniable is the rate of change is happening faster and faster and faster, and it kind of blows my mind, and I love it. So I'm going to introduce the researchers in a moment, but first, and they're going to make us all a little bit smarter tonight, but so a little bit of show of hands here. First of all, who here is from out of town? Nobody. You're all, a couple. Okay, just the Queen's people. Great. Welcome to the warmth. It's a little cold in Kingston right now, I understand, right now. Who all here are Queen's grads? Hands up. All right. Next, who's not a Queen's grad but wishes they were? Nobody, all right. And then finally, who's now figured out they're actually in the wrong lecture and they should be somewhere else right now? All right, let me tell you a little bit about the format. we're going to do, I am going to shut up, I promise. And these guys are going to come up. Each of them will do about a 18-minute, kind of like a TED Talk type of thing. And as you know, we have a second evening for this as well, tomorrow evening. Tomorrow we're going to get into a kind of a fireside chat and get into it in great detail. But this evening we'll also have a Q&A session as well. So when both of them are finished speaking, we'll come up for about, the three of us, for about 15, 20 minutes, give you a chance to ask those questions and not have to wait till tomorrow, some of the things that are top of mind. So with that being done and the format being covered, let me introduce our first speaker, and that is Dr. Ahmed Hassan. Dr. Hassan is of the Queen's School of Computing, and he focuses on researching the intersection of systems and software in engineering. His work is dedicated to making life easier for people who produce, maintain, and evolve large-scale complex software systems. He is the NSERC RIM Industrial Research Chair in Software Engineering for ultra-large-scale systems, that's a mouthful, and the Canada Research Chair for Software Analytics. The tools and techniques that Ahmed has developed are integrated into products used by literally millions of people worldwide. And just talking to him earlier, he literally travels the world to kind of support that. So with no further ado, let me welcome Ahmed. Thank you.
Okay. So it's always good to come to the Bay Area. I actually, my first job was at IBM Almaden, at IBM Research. So it's very nice. I really enjoy the idea of actually swimming in the morning here, doing lap swims outdoors, which is much nicer than in Canada, okay? But today I want to talk about something that I've been kind of working on for the last 20 years. So I'm known for, like, outside is for actually how to integrate AI with software development, okay? But what has happened so the idea is how we can make software developers more efficient, you know, think from Copilot kind of stuff, okay? This is something we've been working on for like 20 years, and seeing that rise and the evolution of the technology in the last 5 years is really breathtaking. And as well, especially now, the speed of the technology is getting faster and faster. But what has happened in the last couple of years was generative AI. We believe we're going to a next stage, a stage where anybody could write code, okay? And that's what we call it software for all by all. And I'll give you a very concrete example. So if you have, in your car, you have these windshield wipers, right? And if you have a fancy car, then they will actually be triggered by, so if there's rain, they will actually get triggered and they will actually start doing it, right? And otherwise they will stop. The old software was very complex. But then now a lot of the new cars, there's a good amount of them that what they do is they have an AI model that's trained on pictures of windshields with rain, pictures with windshield without rain. And there's a camera on the windshield taking pictures every millisecond, puts it for the AI model. The AI model says, oh, this is a windshield with rain, run the windshield wiper, okay? Now the problem is you're driving on the highway, the sun is hitting the windshield. The AI model never saw that picture, and it says, oh, okay, it's raining, but it's not raining, okay? In the old days, to fix that, we would bring in a lot of software engineers, and they would actually have to write a lot of code. But the way to fix this today is you take a picture, you take 20 more pictures, and you say, these are pictures of windshield and sun hitting it. There is no rain here. Which means anybody, your grandpa, grandma, anybody can now write software. Okay? So with that in mind, and I'm starting with this, does that mean this is the end of software engineering? So I'm a software engineering professor. Okay, I'm out of business. What I'm going to convince you in the next little while, this is not the end. This is actually the golden age of software engineering and computing. Okay? The way I think it today is really what I would call is the calculator moment of the software industry. And to give you a very concrete example of that. So when calculators were created, we didn't collect all the math professors, put them on a boat and send them down to Siberia. Okay, we still have them. Okay? But instead, math professors and mathematicians started doing the cool, exciting stuff, and they stopped adding big numbers. Okay? People can do that at home. Okay? Same thing. When Excel was created, we didn't say, okay, all accountants, we don't need any more accountants. Everybody can do their taxes using Excel. Same thing happened. 90% of the world can do their accounting and the bookkeeping by themselves, and the 10% bring in the software, the accountants to do the interesting stuff, right? And if you're a software developer, I'm not sure how many people are in the software industry, I can assure you, it is a very boring life as a software developer. There's a lot of annoying things you have to do. Okay? And the fact we don't have to do these, we can now start doing more interesting stuff. We can start building considerably more complex software. Okay? And this is why we believe that this is really the beginning of something much bigger. Okay? Many people can code, and as well the people that are really good at coding and trained on it can build much bigger things to enable these people to even do more complex things. Now, well, this is very nice, and why should we believe you? Okay? I'm going to give you an example from chess. Anybody know what this is? This picture is? Okay. So on this side here, which you don't see, is Deep Blue by IBM. Okay. And Deep Blue was playing chess against Garry Kasparov. Okay. This was kind of a very historical moment because for the first time, AI, computer, can actually beat a human. Okay, a grandmaster. And today, if you think about it, AI has solved chess. Actually, AI has solved chess, AI has solved Go, but I can tell you, today is the golden age of chess. Many people playing chess. So what happened? If that's the case, so now we're saying AI is going to solve coding, well, then AI has solved chess too. What has happened after this game is Garry played 2 other tournaments. In one tournament, he said, any grandmaster can come and play, and they can bring their AI with them. Bring your computer, In the old days, these were very big computers, okay? You could drag it around with you, bring it in, and we'll play against each other. So that was an okay tournament. The next tournament, which is really exciting, he said, anybody in the world can come play against us grandmasters, and you can bring your AI. And the shocker here was that the people who won this tournament were amateurs. Okay? They were not the grandmasters. And the reasons they won that is because they figured how to use the tool right. They changed the process. Okay? So if you today are going to take AI, and the way I tell everybody is there are 2 kind of versions of this, how to use AI. Take what you're using today and find everything in it and make it with AI, so speed it up with AI, or to rethink the whole process of what you're doing and actually rethink the process end to end. And to be very concrete, so, for example, a lot of the automated driving cars, so, so originally these cars, what they did is they use AI, and what they did is they have a lot of AI to recognize, okay, this is a tree, this is a pedestrian, this is a car, and then they write a lot of code to figure out should we go or stop, right? This is what I would call, automation 2.0. So you're taking what you were doing, just adding, spices of AI everywhere. The next thing was, well, we don't really care about trees and cars. What we really care is should we go forward or stop? That's what we want. So instead, if we solve the problem, it says, I don't care how you're going to reach that decision. Just tell me, do I go or stop? And let the AI spend the time doing all the crazy thinking, you can build much more complex software. And this is something that has even done in sports. And I want to show you kind of the evolution of sports as well to give you some more analogies to make you start thinking that way. Because my goal today is, I don't want to talk too much about computers and low-level stuff. I want to really give you the inspirations to go back and think in your own businesses how to think about that. So this graph here shows the number of broken records per year in Olympics and World Championship for swimming. Okay. Now there are 2 spikes you can see. Okay. So kind of in the early, in the late 70s, mid 70s, and there's another spike around 2008. Can anybody guess what was a technology that was created in swimming that led in that year to so many world records being broken? We can be interactive. Okay. And usually people tell me swimming trunks. People swam with swimming trunks for a long time, okay? So it wasn't swimming trunks. Actually, swimming trunks slow you down. So what do you think happened in, in kind of the late 70s? No, it was something that swimmers have on. I'm telling you, swimmers don't have a lot of things on them. Not the wetsuit, the goggles. It's amazing what you can do, you can see in front of you. Okay? Now, there was another spike that happened in 2008. Can anybody guess that one? Actually, somebody already mentioned it. So it was this special swimming suit that was created, okay? It was NASA. It emulates the skin of a shark. Actually, that swimming suit gives you very high buoyancy, and you cannot use that swimming suit in Olympic swimming. Actually, in any competitive swimming, it's actually illegal, okay? It makes you run way, way faster. It was in the Beijing Olympics. So there's a lot of records that were broken during the Beijing Olympics that till very recently nobody could break them. Okay? So these are two examples where we have done a technology, we've kind of what we're doing, and we just figured out how to speed it up, right? Now I want to give you another technology or another innovation that was not about taking what we're doing and making it better, but actually rethinking what we're doing altogether. Okay? So this is the Mexico Olympics, okay? And this is something, so this is high jump. In the old days, the way people did high jump is they ran and they jumped forward, okay? So it's called the straddle technique, okay? Then this crazy guy, Fosbury, said, no, I'm gonna jump backwards, okay? He was the first guy to ever think of jumping backwards. Today, high jump, everybody jumps backwards, okay? And interestingly too, this was the only medal that he won. He was not a top athlete, because since then, everybody started emulating him, and that became the standard, okay? So that's what I'm kind of trying to get people, right? You need to think of how to change the game altogether, okay? Now, let's talk about software development, programming in particular, which is an area, that's my area of expertise. So today, you think of this programming 2.0, which is AI assisted, so this is like the co-pilots. So what's happening today is, unfortunately, humans are not that smart, okay? And we're limited by how complex software we can write, right? So you cannot write a piece of software that has so many if statements and control, and if this, deep if statements, right? Which ends up meaning that if you look at the complexity of the code you can write, so up there, okay, you're limited by how much complex code, which means you're limited by the software you can produce, okay? But with that in mind, what we're doing is we're taking the classical way of building software, which is code is the king. We want to produce code. We want to make it faster for people to produce code, okay? But if you stop out and just jump out of it and say, actually, code was never the goal. Code was just a medium for us to express our intent, okay? And this is kind of what we call, the Fosbury flop kind of way, right? In here, the AI and the developers are having very deep conversations, not about code, not about if statements, not about control and loops and all that, or which libraries to use. You just tell the AI, this is what I want. This is what I'm imagining as an app would look like. And the AI says, okay, I think I got what you want, but let me clarify with you. Let me go back and forth, okay? And then the AI says, okay, I got it now. I'm going to go in the back. I'm going to go loop as crazy, right? And then I'm going to give you the software that you asked for, okay? On this side, there's no code at all being developed or produced. On this one, it's very code heavy, okay? This is what we believe is the future of software development and how people are going to make software, and this is what's going to enable anybody to write software. Now, not only is this the future, today I want to show you a small demo of some of the work we've been working on that to do that, okay? So this one is a demo of actually building an app, okay, a mobile app. We're not going to at all show anybody code. Instead, we're going to show them, they're going to talk to the AI is going to give them ideas, they're going to go back and forth with the AI, discuss it, ask them to remove stuff, roll back everything automatically, and then at the end, you have an app that you want to work with, okay? Ooh. So you're just chatting with the AI. It's only just chatting back and forth, right? So it shows you different options you can work with, so different options you can pick from. Okay, then you say, you know what, I like this app, this idea you have for me. Okay, so it's very different. It's almost like having a partner, an AI partner that's working with you. I have a good idea. So the same way when you actually do renovation at home, right? A designer comes and says, what do you think of this? He says, I like this. Oh, you know what? I don't like this. Oh, now he says, okay, give me some ideas to improve my app. It says, okay, maybe you want to try, you like an idea, okay? So here, I want to be able to customize the theme of my app. So make it like a dark theme, okay? Then I should say, can you add a dark theme toggle on my app, okay? And then boom, over here, the app is regenerated, the code is generated, everything is done in the back, okay? And then you say you don't like it, it's just unroll back, okay? And we're not coding, we're conversing, we're talking back and forth, okay? So this is just a very kind of glimpse of some of the stuff we're working on, okay? Now, I want to end this by saying safety is going to be very important, right? There's no doubt on that. But where we're going to go with safety is a big problem. It's a big challenge moving forward, right? Let's look at cars, okay? When cars were first created, to make sure that cars were safe, the idea was we're going to have a person walking in front of a car with a red flag, which means cars could not go any faster than a person, okay? Well, today we don't have that. So that kind of went out. On the other side, it took 30 years for seat belts to become legislated. Okay? So we're slowly getting there. However, I want to step out and actually tell you the safety aspects and the impact on society is much more enormous than safety. It's not about, oh, the AI is hallucinating, not giving the right thing. It's actually going to change the whole economics of the dependencies in the whole world, right? Today, there are countries in the world that have very smart people, but with very low income, where people actually go there, outsource development there, okay? When that type of development outsourcing is gone, what's going to happen to these smart people, okay? So that's one thing. Today, if you don't have access to this type of computing, you have a lot of computing needed, there's a limit to how much you can do, which is very different because computing and software development in general was something so amazing that anybody could open a laptop and start coding. We are going past that. You need to have access to a big data center, to big infrastructures to enable that, okay? So today I kind of give you a glimpse of what we're kind of trying to do here is we're really trying to rethink computing in this new world. Actually, earlier today, we had a whole retreat for my School of Computing, where we're trying to think how we can rethink our programs to first enable people to develop software with AI as a partner, and second, to build software that has no code anymore. It's all AI. Okay, so thank you for your time.
Well, thank you, Ahmed. You gave us a lot to think about. And we'll have a Q&A session a little bit later, but I'm certain one of the questions is going to be, you alluded to it about what is all this going to do to the profession of software programming, but also maybe starting to think about what does that mean in terms of what you teach at university, given the amount of change which is going on. But we'll get into that a little bit later. I now want to introduce our next speaker, Dr. Ryan Grant. Dr. Grant is of the Smith Engineering, is on a mission to turn Canada into a global supercomputing powerhouse. His research focuses on the high-performance networking and performance management for extreme-scale systems. His work is being used in every currently announced and upcoming system of the exascale computing era. He's an assistant professor of electrical and computing engineering at Smith Engineering and an R&D 100 award winner. So please help me welcome Dr. Ryan Grant.
So let's talk about supercomputers. Supercomputers do an awful lot for us every day, and we don't realize it. Supercomputers are the AI factories, but they do even more than that in terms of digital twins and other types of simulations. Why am I showing you pictures of rocks? Here's an example of what a supercomputer can do for you. In just a few weeks, as a collaboration between Bay Area companies and large labs, Supercomputer found 30 times more minerals than had been discovered in all of human history, just by looking through and sorting solutions. So there's something supercomputer can do for you, right? But you might say, well, what does 30,000 new minerals do for me, right? I mean, how's that going to impact my life? And so here's some way that it impacts your life. These are cancer cells. Supercomputers can do digital twins of your body, and they can tell you if you have cancer in a certain portion of your body. We can model literally every single red blood cell in your body, all the veins, all of the arteries. And we can do simulation that will tell us if part of these cancer cells break off, where are they likely to land in the rest of your body. This tells us where to look for metastasization when we're looking into individualized healthcare. Right? They can do more than just cancer care as well, but individualized healthcare, all supercomputing. You're gonna have a supercomputer at your hospital in the future, sometime in the future. What's another thing that supercomputing can do for us? New materials, new technologies. So this one's from the Bay Area. This is a collaboration between Google and Lawrence Berkeley National Laboratory. In just a few weeks, they found hundreds of new materials for green applications. Either they're more efficient to use, they're lower CO2 emissions, they could be used for renewable energy. Lots of different materials in this space as well. So what are supercomputers doing for you today? All of this is what they're doing for you today. And some of it, like personalized medicine, they may do for you tomorrow. They also do all of our AI, right? So all AI is enabled by supercomputing technologies as well. This is not new. We've been doing this for ages, right? Some of the oldest computers at this location where we currently are were originally supercomputers, right? So everybody always wanted to get the most compute that they possibly could from a supercomputer. Just now we're in completely different orders of magnitude than we were in the past. So what is a supercomputer really made up of? I've used the word supercomputer, but I haven't really defined it for you yet, right? What's the basis? A supercomputer starts with a fairly regular commercial server. So regular commercial rack server, great, we have one of them, right? The real power of a supercomputer is unlocked by an area that we work on here at Queen's, which is networks. So the power is not in the individual computer. The power is in wiring together multiple different computers with very high-speed networks. Once we do that, computers can work collaboratively. Okay? So if we just put a whole bunch of computers in a data center, we can create a very large capacity. These are called capacity systems to be able to do things. Think about this as the Netflix or the YouTubes or the Google searches of the world, right? I have to do a whole bunch of tasks that are all distinct. Everybody here in the room or everybody out there on the web can all do a Google search right now, and they're all independent tasks. One person's Google search doesn't depend on another person's Google search, right? So I can build capacity without having to have these different computers talk to each other at all. Supercomputers really are the capability class systems. We refer them as capability class systems because they give us new capabilities that other types of computers don't have. So what is AI? AI was a capability that we got from being able to make supercomputers large enough that they could crunch through enough compute to make them useful enough to be able to chat to you, right? So it's simply a compute capacity problem that we're trying to solve, right? We could think about this as an example from Livermore or Frontier. So Frontier is the #2 supercomputer in the world. It's out in Oak Ridge, Tennessee at Oak Ridge National Laboratory. And if you take your laptop and you work on a problem, what you can solve mathematically in your laptop in about 4 years, Frontier does in about 53 seconds. So that's a huge difference in capacity between these two systems, right? And how does it do it? It does it by talking to each other. Okay, so we'll talk a little bit about networks, but let's think about what this actually means. Here's an example. Okay, I own a restaurant and I want to make burgers, right? Somebody comes to me and says, we need to figure out how to make 1,000 times more burgers. And I say, great. Get lots more people, right? Make a lot more burgers, and we'll have 100 restaurants, and we'll have 1,000 chefs, and we'll make 1,000 times more burgers, right? Great, hopefully we'll sell all of them, right? This is hard though. Okay, so I need to make a burger 1,000 times faster than we currently make them. I just need one, but I need it made 1,000 times faster than we can currently make it, right? You might say physically impossible in this analogy, probably true. But if we convert that over and we say instead, everybody in this room needs to calculate a sum of numbers. And I split them up and I give everybody 50 numbers. You sum up your individual numbers. But now we have to find the universal sum of that number here in the room. What's the key bottleneck that we'll have? How you communicate with each other to tell everybody else what your number was so that everybody gets the sum, right? Communication is the key in supercomputing. And what is communication? Communication is networks. So to put that in perspective, a network on a supercomputer is typically the only component that we purpose build in each generation. So companies sell specific purpose-made networks for supercomputing. You've seen bleed over in this recently. NVIDIA sells InfiniBand, the Mellanox product line, to everybody now. That was originally a supercomputing product. I worked on it in the early 2000s when it was just a supercomputing exclusive product, right? But it's now bled into the mainstream. The key to these networks is the following. The networks as we have them for supercomputers rely on the fact that we can communicate quickly in terms of latency. What does latency really mean? Latency is the time it takes me to send my data to you, something info of value to you, and you receive it and acknowledge it, okay? So it's the difference between me sending a letter to you and me sending an instant message to you. Supercomputers are the instant message. We actually work about 1,000 times faster in terms of latency than a typical commercial network. Bandwidths are normally only 2x, about twice as high as a traditional network. But these network cards are expensive. What we've worked at Queen's, and I've worked at it for a long time, is building the interfaces that express how you use these networks through software to hardware. It's the key to how we get from point A to point B with regards to do that 1,000x better latency that we have. We cut out a lot of stuff in between, and we do a whole bunch of fancy stuff to be able to enable those things, but that's the way that we build very high-speed supercomputers and actually get them to work together. We're always building new networks. Now, what does this really mean, right? We talked about the 4 years versus 53 seconds to compute, but there's a lot of terminology behind these things. So during my introduction, you heard about exascale class supercomputers. What does that really mean? Supercomputers worldwide are ranked based on how fast they can do certain calculations, mathematical calculations. Dense linear algebra actually is the main one, even though people don't use it as much anymore. And what they're ranked on is how many floating point operations they can do every second. Basically, how many decimal numbers can you multiply together in a second, right? Your laptop working at gigahertz speeds can calculate billions of flops, floating point operations, per second, right? If you go home and you've got a PlayStation or the kids have an Xbox Series X, whatever it happens to be, that graphics unit will process teraflops, so thousands of billions of calculations per second. A reasonable supercomputer in this day and age will calculate petaflops. That's millions of billions of operations per second, right? And the best systems in the world, and only a few have achieved this, are actually at the exaflop era. That's a billion calculations per second. That can be hard to think of. We think, well, what are the practical ramifications of this? And if we take an example here from the Bay Area, we've been able to do in the past simulations about earthquakes. Okay? And we've been able to look at the entire Bay Area, been able to basically design out the buildings, shake them, and see what happened to the different buildings. And everybody said, oh my goodness, really tall buildings are in danger of earthquakes in the Bay Area, right? That's because in the past, with petaflop computers, we were able to model the ground as basically just ground, right? It was one solid object. Exascale let us model the ground as multiple different layers of what the ground actually is and all the interactions between those different layers of the ground. So now we can find out that in the Bay Area, medium-sized buildings, medium-story buildings are actually in more danger because of where they're located, and the ground underneath can liquefy. Why? Because now we can simulate all the different parts of the ground actually rubbing against each other and what actually happens in that physics. So supercomputers provide us a way of understanding our world and understanding it better as well. And in the future, Yes, you're going to see AI models do a whole bunch of interesting stuff as well in helping us understand these things, but you can see a lot of traditional digital twins and simulations as well. Let's talk about AI for a second, or more than a second. So AI is basically a big, gigantic compute problem, right? So it's the equivalent of take everything that everybody ever wrote on the internet and shove it into a model, look at the data that's available for it, and crunch it. Basically make some sort of coherence between it, right? It's a big, gigantic correlation machine, essentially. Oh, excuse me. I am greatly oversimplifying all of AI by saying it is a correlation machine, but just bear with me for a second when I say, essentially it is trying to correlate and predict the probability of outputs based on inputs that we have. When you use this in a supercomputer, though, one of the biggest challenges to everything that we do in a supercomputer, because it's made up of many, many other computers, is how do you chop up your problem? How do you actually make the problem small enough that each computer has enough work to do, but then you can add that all together to make one big problem as a whole, right? The simplest way to think about this is traditional simulation. When we do simulation of your body or whatnot, I guess what we actually do, we actually chop it into really, really small cubes, and then we just use those really small cubes as a representation of the actual physical world. It works as long as you make the cubes small enough, okay? AI has the same problem. We have a gigantic amount of input data, and we need to create a very large model, and we need to be able to figure out how we chop these things up and make them work. So what do we do first? One of the methods is you chop up your data. So you chop up your data and give it into each individual computer or each individual GPU, and you go from there. That's data parallelism. You can also do model parallelism, where you share the data, but then you chop up different portions of the model, and you recombine them later into the one larger model. How you chop that up is the difference between what some people call model parallelism and other people call tensor parallelism, but basically it's essentially the same task. We take a really big problem, we chop it up, we assign it out to different portions of the supercomputer. They all have to talk to each other because they're collaboratively working on one big problem, and then we eventually recombine everything back together to get the end solution that we want. So AI is essentially a supercomputing problem as well. The difference is that now everybody wants to spend billions of dollars in supercomputing, where 20 years ago, mostly governments wanted to spend money on supercomputing. Why did governments want to spend money on supercomputing? Let's talk about the global landscape of supercomputing for a second. The Japanese, for instance, are big into supercomputing. What do? Things that you would expect the Japanese to do: earthquake modeling and tsunami prediction, things that really matter to them, right? That's not something that a private business is going to do, but it's something that a government would like to do. The US uses it for plenty of different things: fundamental scientific research, national security, defense, all sorts of things get used for supercomputers in that space, and the US typically leads the world in terms of total supercomputing power. Right now they have more than 4 exaflops of total power deployed in this in the country. We have Europe that heavily uses supercomputing as well. Europe has some interesting use cases. They use it not just for research, but for example, Italy's biggest supercomputing user is their power utility. Why? It's really useful for them to make a whole bunch of money off of it because they maximize their grid through supercomputers. They've been doing that for a really, really long time, right? The French use it for a variety of different tasks, so do the UK, very large supercomputers over in Europe as well. So where does Canada stand in all of this? So before I tell you where Canada is, let me say part of my role at Queen's is fixing this problem. So our top supercomputer in Canada lies at, I think, 154 on the list as we count it right now. We're behind Poland, we're behind Brazil. We're like competitive with Czechoslovakia in terms of our overall compute. But of course, Poland and Czechoslovakia aren't entirely fair because they have access to all the EU supercomputers. They actually have way more compute than we do. Now, the government has recently announced $2 billion to spend on AI infrastructure and compute. A lot of that is going to public research infrastructure as well as innovation supercomputing. We at Queen's have been very hard at work trying to build next generation large-scale AI systems. It's not going to be a $100 billion investment or 100 billion euro investment like the EU, but you'd be amazed at what you can do with small amounts of money when you're not the first to arrive at a brand new technology. And so what we're trying to do is build a top 20 supercomputer. 20 is pretty good, right? In Canada, on Queen's campus, for both industrial innovation with our industrial partners, as well as research, and enable AI education on campus as well. So we want to be one of the first universities that brings in real large-scale AI to teach it in classrooms and have students understand what they need to do to build out large AI infrastructure. So we want to teach people how to build these systems, because not a lot of people are out there training people on how to build these systems. They're out there building very large systems. I recently returned to Canada specifically to do this because I used to work on very large systems. And now I want to educate the next generation in these systems as well. So with that, I will leave you with the last Easter egg, which you've probably noticed. There are inconsistencies in some of these pictures. This presentation is entirely AI done. I did that not because I'm lazy, but because I wanted to demonstrate to all of you that it's pretty good if you don't look very closely at where we are today. This is an actual application of supercomputing itself is this presentation, aside from what I said. So with that, thank you.
This is the part where you guys participate. And what I'd love to do is get some questions from you. So just let's dig in. Fire away. Number one. There's by the way, microphone so that everyone else can hear you.
Hi, Douglas Chan, Psi 98. The question about the supercomputer ranking, I am surprised I didn't really keep tab on how Canada is rated. Just wondering, what is what do you call it, a stopgap thing that we need to do to bring Canada or Queens up 100 times 100 rank? You mentioned we're building something. Is it just a matter of putting money in it? What are the technical obstacles?
That's a great question. So is it a matter of just spending money? No. Supercomputers are hard to design well and deploy well. So there are some upgrades that are happening to our digital research infrastructure right now that should come in significantly higher than where we are right now, but we don't expect those to come into the top 20 at all. So what do we really need to do to get into the top 20? We need to start investing in expertise. So Queen's is actively recruiting more professors in supercomputing right now to add more expertise in the area. And we need to commit to training people. So we know those graduates will be very popular. All my PhD students do quite well. A lot of them end up in the Bay Area. But hopefully we can retain a few of those that still want to work in Canada and build systems in Canada as well. So that's part of the reason why we're not just saying, hey, just spend $2 billion and we can build a top 1 supercomputer. Building a top 1 supercomputer typically involves inventing new technology. We're not quite there yet in terms of our expertise. We probably will be in 10-ish years by the time I can train a lot more people in the area and we can bring in new people as well. So part of the challenge is just building out the new technical expertise, retaining that technical expertise, and then actually building and buying systems. That being said, we're proposing some smaller systems for immediate impact. So there's a smaller system which, if deployed right now, would be significantly the largest supercomputer in Canada that we're trying to do by fall, for instance, if government funding comes through on it. And that large top 20 system is in a two-year-ish time frame in terms of building it. How? The supercomputing community internationally is very collaborative. We work together an awful lot. So it's also not just us putting together a supercomputer, it's our international partners putting together a supercomputer with us. And that means that we can share the load a little bit. Everybody loves building a new supercomputer. Everyone of us is a supercomputer nerd and we love building them. Everybody's like, oh, somebody's building something new? Well, I gotta go over and work there for a little bit and help them out for a little while. So those are sort of the barriers that we're trying to get through. It's not just money, it's really about expertise and choosing the right people to build it and architect it so that you get all the money out the tail end in terms of productivity. There's nothing worse than building a supercomputer and not knowing how to use it, and then you just end up wasting your money. So yeah, those are the main challenges. So we're hoping to resolve all of those challenges over the next few years, get Canada back to where it should be in terms of the ranking as a G7 nation. And you know, we're never gonna punch above our weight with regards to, we're never gonna compete with the US, 10 times as large as we are. but we want to make sure that we're punching equal weight in terms of our population difference.
Some other question? Yes, right here.
So, Ahmed, I have a question for you. It's focused on your final slide around programming kind of 3.0. And I wonder if you would agree with this. Is the future of programming where it really just homogenizes with every other instance where we just ask AI to make stuff? So if I say, I've got chicken and lemons and I want a recipe, or I say, make me a video of a dog riding a bike, or make me a to-do task management app, you know, it's just digital output. So I'm just asking for stuff. And that asking for stuff, it gets interesting when it really kind of tips from pure digital asset to physical, like asking AI, hey, take me to Waymo, take me to the Opera House. Or I'm sick of this ketchup bottle tipping over when I'm trying to get the last of it. Look at this, and could you 3D print me something that would hold it up? Like anything, like, it's just asking for stuff. So does programming 3.0 plus just means that it's not programming? Forget the word programming. It's just AI making stuff that we ask for.
So not all software is created the same, right? So the software is going to kind of, for the airplane, is going to be very different than the macros in Excel, correct? And AI today is kind of where Excel macros, right? So I guess it's more like 2C versus 2B, right? So mission critical stuff, we're quite far from that, right? But, you know, simple stuff, simple scripts, you want a quick app, you know, today when you use your phone, you do many things together and you would like to create a quick app for that, and you're willing to forgive it, which is the key thing, actually. The key thing is we're moving from this idea where software is always right to software that learns and grows with you. Okay? Same way when you hire an intern, okay, and you ask them, hey, go get me a coffee, and they go give you a decaf. Okay? Then you tell them, no, I want real coffee, okay? And then next time, if they do it again, then you're unhappy with it, okay? Very different way of how we think of, you know, software, which is it learns with you and grows with you, okay? And then the second part is, you know, there will still be, so for example, Waymo, I think you mentioned Waymo, right? So Waymo has tons of AI, but I can assure you, you know, little kids and your grandparents and, you know, are not programming that, okay? There's a lot of work that needs to make this trustworthy, safe, and this is very far away. But it basically enables you to do a lot of things. The best way I like to call it is software, like software makers. You know the whole maker idea, everybody can get a 3D printer and you can make stuff. Yeah, you can make stuff, but you can't print bridges. So this is where we are.
Thank you. Hugh, did you have a question at the back?
This question's for Ryan. It seems to me that the software you have to develop for that supercomputer has to either, you know, be open source or something so that you can take advantage of what other people are doing. And in that software, you've got to break down the problem and assign the compute problem to different computers. So is there logic in your software that determines how to break that software, the problem down, depending on what the problem is? You know, does it look at the structure of the problem to do that?
Sure, great question. So there's multiple different levels at which we actually break these things down. So the first one is the application. The application itself has to decide on what shape its problem is and what size it's going to assign to each node. We help this out with the communication libraries that I write. So when you start up your application, you can define, okay, great. Each different server or each process on each server gets a special number. We break up the problem based on all of their ID numbers. It's a much easier way to break up your problem. And then the communication software that we write underneath it is things that are all open source. So we contribute to a couple different major communication libraries. The first is called the message passing interface. 97% plus of all scientific software in the world runs on MPI. We contribute heavily to MPI. I wrote a chapter of the spec. We improve that library literally every day. It's all open source. You can download it right now. You can contribute to it if you'd like right now. The other library that we contribute to is Nickel. And by extension, every once in a while, RICL for AMD as well. Nickel is the NVIDIA collective communications library. We also contribute over there for individual GPU type communications and improving the efficiency of those systems as well. It has the same basic idea of you can break problems down. When you boot up an application, the first thing we do in the communications library space is we assign you all the numbers and we tell you who everybody is. Once you've done that, it's a lot easier algorithmically in your application to figure out how you're going to break up your problem. A few of those elements still end up being broken up in the application themselves, but then when you need to exchange data, we've spent, far more time than I have been contributing to the community, decades, optimizing how the different elements of that compute communicate with each other in the most efficient way possible. So Nickel, literally the first author of Nickel was Sylvain Jogi, who was from the OpenMPI community, the system that I contribute to greatly as well. It's a lot of those same ideas that came from the scientific world applied specifically to NVIDIA type hardware. Same with RICL as well. So we all open source things, we collaboratively work together. A lot of those same ideas and optimizations get rolled into things as well. But ultimately, the application decides that high level, what does my cube look like and how many subcubes should I have? Then we figure out for you how you can effectively communicate. And if you get it wrong, we can occasionally tell you you got it wrong as well. So that's how we tune large-scale scientific and AI software.
Cool. We probably got time for one or two more questions. Over here, right. Fire away.
Yes, thank you very much. Fascinating presentation. So I know Queens is right across the water from Wolf Island, and I'm just wondering about what the green impact, the energy consumption of such a compute cluster has from an energy perspective, and whether, or what is the amount of thought that is being given to making it efficient from an energy perspective, and not just, I guess, throw away a lot of the energy in the form of heat, or whatever that might be. First question. The second question is, as far as convergence of quantum compute to what we're trying to achieve here, and whether that's going to intercept within this generation of compute, or is it something further down the road, and whether there's an eye to that and being able to include that when it is somewhat ready for prime time.
Okay, two great questions. So to give you an idea of how green we're trying to build this data center, I do lead a global effort that is about power and energy control and monitoring on supercomputers. We just released some new versions of it with dealing with liquid cooling controls and what we can possibly do in that space. So what will we do with a supercomputer on campus? If we talk about a supercomputer about the size that we're talking about, they're about 5 megawatts each. So we can build up to about 5 of them. So you're somewhere between 20 to 40 megawatts worth of power. Once you get up to about 15 megawatts of power, that's about all of the power that Queens consumes as a campus right now. But you may have noticed at Queens that there are a lot of radiators all over the place, because Queens is primarily heated by hot water from the steam plant down by the water, down by the lake, in addition to KGH. So we've been looking into how we can reuse the heat for heating the buildings over the winter. It's really cold right now. We could use some extra heat, right? And in the summer, we've been looking at some unique things that we might be able to do with some of the geothermal that we have just down the road at St. Mary's the Lake, as well as other ways that we could recapture some of that heat and reuse it. So I regard any heat that's recaptured and reused as an electron used twice, which is fantastic efficiency, right? You use an electron twice, that's great. We've been exploring some new technologies about how we could build one of the first chillerless data centers in the world, and exploring the greenness of the overall center. Of course, part of this is power in needs to be green enough to have compute out to be green enough as well. If you look at the Ontario power grid just as a whole, so we'll just neglect Wolf Island for a second, but they could be a supplier that's 100% green, no CO2 emissions. If you look at the Ontario grid, it is vastly dominated by nuclear power and hydroelectric power, much over 90%. And so almost all of Ontario's power is essentially almost CO2 neutral to begin with. So regardless of whether we take the power directly from the grid, we supplement that with some green power that we can have, and we go over that with chillerless solutions, we can make a center that uses very little water, reuses all of its power, or as much as we possibly can for waste heat, and demonstrates new technologies to the rest of the world about how you build a green data center. So some really innovative new stuff that we plan on doing there, both with partners in the space as well as partners potentially in industry that I can't talk about right now because none of that's finalized. The question about quantum computing, I guarantee you I'm going to get this wrong because just yesterday, Microsoft changed my answer. So I'm going to give you a different answer today than I would have at like 6 a.m. this morning. So quantum computing is a fantastic accelerator to supercomputers. It can solve some problems that supercomputers are not good at solving. But a quantum computer can solve your, find the prime of this ridiculously long number as fast as it can do 8 plus 5. Right? Well, traditional computers are still, we're going to use them for 8 plus 5. We're going to use quantum computers to solve my primes or solve an NP hard problem in that space, right? So quantum computing really is an accelerator. To give you an idea of how we view quantum computing, there is on the blueprint right now for the center, and it's a rough blueprint, a noise isolation and vibration isolation pad specifically to install quantum in the future. So we're thinking about how quantum gets into that center, but it's not clear whether that's going to be a 5, 10, or 15-year plan. So we're preparing for the future, just like we're preparing for future cooling technologies as well. But that's not going to happen in the first generation. So I don't anticipate installing a quantum computer day one. I could see installing one within 5 to 10 years, though.
Very cool. Any other questions from the crowd here this evening? Yes, all right.
Maybe one question back to Ahmed. You mentioned that mission critical applications aren't really appropriate yet for this, but as you start thinking about things like medical devices, airplanes, like firmware that actually operates so many critical capabilities in our society, when do you see that changing? Is that kind of the next wave of this, or is that even further down the road?
So I guess the biggest problem right now is that technology is moving at a much faster rate than I've ever seen, right? So it's hard to say 10 years horizon, but I would say for sure the next 5 years it won't be happening. At least it won't be widespread, or at least you need the people that are trained to do it. So like the Waymo example, right? So cars using a lot of AI, at least I wrote it, I felt quite safe in that type of car, right? But, you know, ride a Tesla and have it on fully automated driving, it's a bit more freaky, right? And then, you know, a Ford is even worse, right? So you need to have people, the big problem today is we are not training software developers and computing folks to really program for that type of software, right? The probabilistic nature is a very different way to program versus here's a piece of code, I know exactly the inputs, I know the outputs, right? So we need to really train people. We need to learn how to actually make software out of this AI that's kind of out of control. Or, you know, a lot of times you can think of a lot of these large language models today, people think of it as like an alien came out from space. And we're still trying to poke it to understand how it works, okay? So that's one thing, we're still in the poking phase. Second, after that, we need to figure out how to control it. So almost creating like a bubble, a safety bubble. But at the speed that things are going, and especially enables collaboration across the world, open source, I think we're moving much faster. Say in a 5-year horizon, many people will be able to do it. So today there are some companies that can do it and are doing it really well, but making that on a wide scale is still something that's not something you can pull out very easily. We don't have people trained to do that yet at this moment. And actually that's what I was talking about. So we had a retreat for the School of Computing earlier today, so the whole morning I was stuck on, on a Zoom call, right? So basically trying to figure out how do you change computing to enable people to build that software in a trustworthy manner. That's one. And second, how to actually make sure that, how do you train people to work in a world where some of your collaborators are pure AI, right? And how do you collaborate with AI and work together with it?
All right. Just from a format point of view, we're not kicking everybody out. We're going to end this in a few minutes, and these two fine gentlemen are going to be around. You have an opportunity to network and ask them some more questions. But we have time for one more. Any more burning questions that can't wait for right now? Anybody? One more. Fire away. Yeah.
So sort of a general question in terms of, lots of innovative technology and research happening, but has Queen's given any thought to, how do they commercialize some of the early opportunities that come along?
You want to go first, and then I'll go?
So commercializing like some of the technologies that we develop, you mean out of?
Well, the outputs of AI and the outputs of this supercomputing into commercial opportunities,
I think he has a very good business plan. I'll let him do that, and I'll do my quick one.
Sure. So I would put it this way, that there are two outputs from an innovation supercomputer, right? One is business work. And obviously that results in a lot of patents. Everybody wants to protect their work. It results in a lot of fundamental returns on investment with regards to supercomputing. So when you look at the math, you look at the surveys that have been done out of Europe or the US, generally every dollar that gets put into a supercomputer results in $40 to $60 worth of profit, depending on your area that you're working in and your particular field. So lots of money gets made in supercomputing. From a Queen's perspective, I would put it this way. I have had a successful career in giving away my technologies by patenting them and then giving away licenses for $1 for the following reasons. Companies like to know that they have good technology that they can use, and they're willing to build off of technology that they know that they can use. But when I build things out that are standards or improvements to software and that sort of stuff, I actually want everybody to use them. I don't want one company to come in and say, great, I own that now, right? And everybody does this thing. I want to actually encourage the market as a whole to more broadly adopt things. That's part of the reason that you've seen, at least from our work, more penetration into a larger number of manufacturers in the supercomputing space. So I kind of look at it as, think of me as the frontier of research in that space. I want to make sure that everybody's coming along with us, and so I want to facilitate not commercializing that technology. The tail end and the benefit to society and Canada as a whole comes in all the businesses after that using that technology, right? Businesses are going to invent their own technology as well. I'm a software guy. I make software. I teach people that do hardware as well how best to design some of their hardware, but I don't tell them how to design their hardware. They design it, they sell it, right? It works with the software interfaces that I have. I want that to be broadly available to everybody, so it's not just some secret sauce, right? So standardization is still a thing, and in supercomputing at least, we get along well enough that we can try to standardize things. One of the most recent developments in that space is Ultra Ethernet and the Ultra Ethernet Consortium. So if you take a look at Ultra Ethernet Consortium, in particular the HPC AI version of Ultra Ethernet, it is remarkably close to some of the work that we've done in the past, and actually some of former alumni who worked on projects that I work on were involved in that as well. So great, we love standardization where it makes sense. We don't want to lock in technologies there as well. If we invent something that's truly revolutionary that we do actually think is a completely viable business, sure, we'll invest in that, don't get me wrong. But my goal is really to give stuff away so that all of you can make money. And I just get to play with the supercomputers, right? So I get to play with my toys. All of you get to make money. Everybody's happy. And hopefully a lot of that money that gets made comes back to the university in research dollars so we can discover new technologies. So it's this nice roundabout cycle where we can create new technology that then leads to new business investment and profit. I'm not interested in going out and commercializing a product. I really don't want to harden it so that customers don't accidentally put the wrong switch into a code and crash the entire system. I'm interested in building the cool thing, and you have to know how to use it. Let somebody else productize it. So from our perspective, it's very open, and we see the tail end benefits in the market on that side. Now, that's not true of all of Queens. There's plenty of commercialization that goes on at Queens as a whole, especially that which is further down the technology front. So I know Ahmed has some experience in that, so
Okay.
let him address that portion.
So the biggest problem, to be honest, is Canadian universities don't have a lot of money. Okay. And a lot of times we end up basically working with companies to enable them. So for example, like a lot of the BlackBerry infrastructure, the stability of the infrastructure, the monitoring is all coming from patents that are coming from from our lab, okay? So that's for very specific tasks. In other times, we would work with open source to big impact. For example, I don't know if many people know. So for example, today, one of the big things, I guess in the Bay Area is something called Ray, which is an infrastructure to basically manage. It's almost like think of it as an operating system for clusters, okay? And we work with them to actually create like the next generation of that infrastructure. And then in case the whole world is benefiting out of it, unfortunately, not a lot comes back to Queens. So I think, if you're an alumni, there's an opportunity here where ideally I would like Queens to have some independent funding that me as researchers could actually go and get that funding and try to make big breakthroughs, have patents that actually can bring money back into university to enable more innovation, more scholarships, and so on. Because right now, the way we're working is, so some companies have long-term vision. So BlackBerry was very good with us. We've had almost a 20-year relation on that, very, very strong vision and long-term vision. But a lot of other companies just want something, 2 days or 6 months, right? So we need to balance both.
I think we'll put a pin in that right now, but I think you've opened up a whole new area of conversation that we might dig into tomorrow night, the whole issue of commercialization, and start thinking about that as it relates to AI and that whole debate that's going on right now in terms of standards and, as you say, some companies wanting to own it, others wanting to share it, and the not-profit approach. So could be a very interesting conversation tomorrow. So we'll put a pin in it right now. Again, these gentlemen are going to be around. Can I get another round of applause for these gentlemen? I'll talk to you about logistics. Thank you, gentlemen. And then just so you know what's happening tomorrow evening, we're going to kind of build on this, but it's going to be more of a fireside chat approach. Please come with some questions and some debates that you'd like to get into. I think we just started to get into one right there, which could be fun to dig in more on. So that format will be a fireside chat, and then we're going to feed you. We've got a nice 3-course dinner afterwards, and we'll have an opportunity. These gentlemen are going to move around. In case you didn't know it, you're going to be moving from table to table. So everyone has a go, as you so to speak. But that'll be tomorrow evening. And then after that, if you haven't been to the museum here, there's an opportunity to get a guided tour of the computer museum here, the history museum here. Doors open at 6. We start at 6:15 tomorrow. Thank you very much. Thank you guys for coming 2 nights in a row. And I think it's a bit of a theme I wanted to talk a little bit about, and that is engagement. And it's great that Queens folks here are getting engaged and showing up for these types of things. Myself, I talked a little about that last night. I've been on the advisory board of the Dean's Arts and Science Advisory Board about 5 years ago. It took me a long time. For those that weren't here last night, I'm Arts 79, and I shudder when I say that, and you can do the math. But it wasn't until about 5 years ago that I got re-engaged, and I really enjoyed that, and that's been great. But as I think about Canadians, there is kind of a theme about Canadians getting engaged and wanting to help. And I've seen that not only with the Queen's world, but there's another program. Anybody here heard of C100? Great. So C100, I'm just going to talk briefly about that. I've been on that for 15 years since it got started. And it was just a collection of Canadians that wanted to help Canadian entrepreneurs in Canada when there was no venture capital in Canada, like almost nothing except BDC. And what we would do is we bring entrepreneurs down here, introduce them to some VCs, do some mentoring. And that's been a great program because, and people like Shopify came through that and others very successfully. That problem's now solved in Canada. There's lots of early stage capital, which is great, but we still have that going on to kind of help connect them to the Valley and people here. Because the cool thing, there's like 300,000 Canadians in the Valley. You've probably heard that before, which would probably make it about like the 10th largest city in the country back in Canada, or something like that. But the other thing I wanted to kind of riff on a little bit, how many have heard of John Stackhouse and Planet Canada? Anybody read that book? Okay, good. So I can tell you about it, and you can have to believe what I said until you read it yourself. John Stackhouse was a Queen's grad, Queen's Journal editor as well, became editor of the Globe and Mail. He wrote a book called Planet Canada about 5 or 6 years ago. And the thesis of that was there's a diaspora, I can never say that word right, of Canadians all around the world. And they're everywhere, and they've done well in whatever profession they've chosen to do, whether it's tech or medicine or what have you. And a common theme is they really want to help. But interestingly enough, they don't get asked enough to help. And Stackhouse called it the 11th province of people out there. And it's, and talking to John about this, and I've seen him speak about this, he's said, look, Canadians as a group are willing to help. And so his advice, and my advice I'm going to just replay as well, is, and this is an advice to the Canadian government and to the universities, is ask for help. And what's interesting is if you ask a lot of Canadians, they'll say, I don't hear from them, I don't get asked to help enough. And they really want to help. The US does a very good job of that, as we know. The Alumni Association, yes, they'll ask you for money, but they'll ask you to help. But people jump in. And my observation, whether it's C100 or Queens, is people want to help. So Queens, ask more. All right? So that's my advice. Anyway. Thank John Stackhouse. He's the guy with the idea. Anyway, on that note, I'm going to bring up our two speakers in a moment. And I'm just going to give you, for those that weren't here, yes, a little bit of background. So first of all, Ahmed Hassan of the Queen's School of Computing spends his time researching the intersection of systems and software and engineering. His work is dedicated to making life easier, thank you, for the people who produce, maintain, and evolve large-scale complex systems. He is the NSERC and RIM Industrial Research Chair in Software Engineering for Ultra-Large-Scale Systems. I still can't get that right. And the Canadian Research Chair for Software Analytics. His tools and techniques, frankly, are used by people quite literally around the world. So, and he travels a lot to do that. So I'm going to ask him to come up in a moment. And then we have Dr. Ryan Grant, who is of the Smith Engineering School. And he's on a mission to turn Canada into a supercomputing powerhouse. And his research focuses on high-performance networking and power management for extreme-scale systems. He can say it a lot better than I can. His work is being used in every currently announced upcoming system of the exascale computing era. So I'm going to ask both of the gentlemen to come on up and join me on stage. And then, so round of applause for these two, please. And what I'm going to do first is ask Ahmed, could you maybe spend 3 minutes and give us the short version of your speech last night without breaking the chair? And yeah.
So the big summary, kind of the big take home is, while AI is becoming very big and every single year is the end of software development, is actually not the end of software. Okay? Think about it, it's almost like the creation of the calculator. When the calculator came up, we didn't fire all mathematicians. When Excel showed up, we didn't fire all the accountants. Instead, people started doing more Excel. But if you're going to use these tools the same way that you're already developing code, which is just, okay, I'm developing this piece of code, please help me produce the code, you will never actually get the full potential of it, right? So that's what's called SE 2.0 and SE 3.0. So SE 2.0 is you take your current process as is, but you but an SE 3.0 instead is you actually rethink the whole process of development. And I give an example of, where a lot of these urban driving companies, originally what they were doing is they were trying to integrate AI. And they were using all this speech recognition to know, okay, here's a pedestrian, here's a car, here's a tree, here's a child. Okay, and then they doing all this, they ran a lot of code to figure out the car should go right, left, we stop, okay? But instead of doing all this, you just tell the AI, just tell me, should I go right, left, or something. Okay? So you kind of remove this, went from, instead of finding, identifying things, so just find out what I want to do next. Okay? And then I ended up showing a demo where any person could actually develop an app by just talking to the software, right? You're talking to an AI teammate and saying, no, I like the app about this, then I will show you immediately that. There's no code, you never see the code, and you're going back to, okay? And the key take homes of this is first, it's actually not the end of software development, it's actually, let's say, the golden age of software development. But the reality is, as an educator, we need to rethink the whole curriculum, how we actually teach software development, software engineering, anything EQ, right? And at least for outside of the school of computing, we're working very hard on trying to rethink that and what exactly that involves in it. Today's discussion, we can talk more about that, what our ideas of how the futures of teaching these people. Because to be honest, sometimes I feel really guilty because I know I'm teaching them stuff that in 6 months, they don't need to, right? Do we need to figure out how to help this thing? So yeah, that's the very quick summary. That's good. Thank you.
All right, Ryan, why don't we get your summary, and then we'll open up for some questions.
I'll start with the short one. Supercomputers are cool. And then we'll go into the slightly longer explanation of that. So we're really seeing a revolution in terms of commercial entities are now really interested in very large compute and very high intensity compute, right? They're interested because they see money to be made in AI. The reality is that supercomputers, very large compute, have been used for decades for very important things, for everything from discovering more about the cosmos, to discovering new materials that we need, discovering new chemical properties, understanding earthquakes, understanding tsunamis, understanding forest fires and how they spread. Supercomputers have actually touched your lives in many, many different ways. I guarantee pretty much everybody in this room has already used a supercomputer today without realizing it. If you check the weather, your weather forecast came from a supercomputer, right? So supercomputers really are about making very large systems that are not just capacity systems. They're not just the Google searches of the world where we can do a billion different searches all at once and we can manage the capacity on our system. They're really about giving us new capabilities, our ability to find out more about the human body, to do personalized medicine, to do cancer care and discovery. In the future, your doctor is going to use a supercomputer to help diagnose you and actually figure out what's wrong with you and then how to treat you as well. Right? So supercomputers are a very interesting way that we're for the first time moving into a new age, right? So the industrial age turned electricity into work, physical work, right? Farm work, weaving cloth, it turned physical energy into physical work. We're now in the new stage where we're able to take energy and turn it into intellectual work of a kind, right? So you can use an AI to do something for you, to talk to a client, to discover something, to do research for you. The sophistication keeps getting better and better, and that's simply because we can make more and more compute. So our goal is not just to make that compute faster. So my lab, my research is very much about making them communicate faster so that all those capabilities, it's really a whole bunch of computers connected together that can actually produce more compute effectively in a larger group. That works for both AI and our digital twins and healthcare, like I was mentioning. And then take that and also make it more green. So supercomputers consume an awful lot of energy and power. So just today we were out touring Lawrence Berkeley, our national lab, and Corey. They are concerned because they use tens of millions of gallons of water a year for a supercomputer. And that's one of the greenest supercomputers on the face of the planet. So what do we need to do in the future to be able to do these things? We're busy at Queen's working towards a very large supercomputer build off of some new government funding. $2.4 billion has been invested in AI infrastructure. And we're working towards building a system that's not only very energy efficient, but is also incredibly water efficient and reuses our heat. So we're looking towards a supercomputer in the future where we can teach students the new reality of being in an AI world and what compute actually means of translating energy into knowledge work, as well as to augment the curriculum as well as just prepare everybody for the future. Because the universities without supercomputers will not be prepared. And then we're also trying to help the Canadian productivity problem and Canadian industry by educating and training them as well and providing a place that they can come to use a large supercomputer as well. So our goal is to build a top 20 supercomputer in Canada, and to have that not just be a one-time thing, but actually have it sustainable and supported by industry such that we can build many more in the future, and all the people around it as well. So we're 153rd, I think, with our best system now. Don't quote me on that. It might be 156. That's not very good. We fall behind Poland and Brazil in terms of total compute power. That's not great. We're 100 times behind the United States, for example, in our public compute power. So we can catch up. We just need more people trained and more people doing that kind of supercomputing work. And I'm looking forward to talking more about that with you today on how we can catch up, how we can eventually become a leader in the longer term in this space. We have the talent, we have the AI talent as well, to be really great leaders in this space. And it's just a matter now of the very hard task of building the infrastructure and the intellectual capacity around it to actually understand how you build and maintain and architect new supercomputers and add to them in the future in wonderful ways. So I look forward to talking with everybody more tonight, yeah, I look forward to conversation.
Great, thanks guys. I'm gonna open it up for questions in a minute. Maybe I'll start with just one question and kind of get things going. Ahmed, just talking about the changes which you covered last night in terms of how software programming is changing and getting, in one sense, easier, but opening up a lot new opportunities. Obviously, that means change not only for the profession of software programming, but also in terms of what we teach and how we teach it at university. So how are you thinking about how you might change a curriculum, or how do you see the curriculum changing for students coming into computer science and programming and whatnot?
Yeah, so, the future we see is there's going to be a lot less people programming day in, day out, right? And instead, the first thing is, instead of writing code, you're going to be reading code, right? And this thing is actually, we never taught people how to read code. We teach them how to write it, but to read it and read large quantities of it is something that people get after years and years of experience, maybe doing code reviewing as professional developers. But now this is going to become an essential skill. So that's one. Second, the School of Computing is very interdisciplinary, so we work with many people across the, different departments across the university, and a lot of people come to us, we teach them, and one of the biggest challenges when people are not into, so there's people with very clean brains, very excited about computing, but as soon as they get frustrated with compilers and all these semicolons and braces, and well, that's gone, right? And now we need to really focus on computational thinking and how to teach computational thinking. And the problem is, the idea was, if we teach them how to program, then somehow they're going to figure out how to do computational thinking. But instead, programming is gone. You need to focus more on the computational thinking, how to structure your thoughts, okay? That's second. Third is, the way these AI things are, the best way I can think about them is like aliens that came from outer space, okay? And unfortunately, a lot of computer scientists don't like talking to anybody, including aliens, okay? But the reality is, if you cannot talk, you cannot express, you cannot understand the communication, now it becomes more complicated, or maybe it's easier. Actually, here's the interesting thing, because this AI never judges you. So we're seeing the symptoms where, for young developers, they're actually very comfortable with that AI. Because they can talk with them, kind of back and forth, and then they have a cool idea, then they go to the big boss, and then I don't have to be embarrassed, right? So it changes the whole dynamics of even how to work in a team, okay? And even the deeper things. So now if you have had your AI partner, and 80% of your time you're working with that AI partner. So now you're going to a new job. Who's going to write your reference letter? Is your AI partner or your boss? So,
All right, interesting.
So it's a total rethink of what it means to do software development, what actually the interactions, and some of the things I'm mentioning here. So we are in computing, so we're a bit ahead of kind of like what's happening in the rest of the, the faculties and departments. It's the same everywhere. No matter what your business you're in, they're going to be talking with these AIs a lot. And then you won't even understand them. You won't correct them. So it's a very different perspective. And, that's actually, I was saying, yesterday we had this whole retreat, and the whole department's trying to figure out, what do we need to do? It's a very complex thing. And, you were saying we should ask for money and stuff. Right? I do believe, quite frankly, that this is probably the biggest challenge moving forward. And for me, like from my research, I have a lot of industrial, collaborations and all that, but I can tell you the impact on education whether it's computing, whether it's engineering, whether it's biology, it's just huge. And people have not clicked in yet. Everybody's excited about, oh, this can do this, but people are gonna have to deal with this. Maybe in 10 years when I present this, half of this room is gonna be AIs, right? And how would you interact with that? So that's just some of the crazy ideas going in my mind right now.
I'm going to open up, by the way, quick clarification. When I talked earlier about ask for help, by the way, I wasn't necessarily talking about money. I was actually talking about time. I mean, I'm sure they would like money too. Money's good too, but in all sincerity, when I was talking about C100, there's people volunteering their time. In fact, people actually give money so that they can volunteer, which is kind of crazy, but also just getting involved with the Queen's community and spending time and helping and mentoring students and whatnot. And I think those are areas that time is, and the knowledge and the experience that you all have is, you have a lot more that you can pass on than you probably realize. And that's really what I was getting at. But anyway, with that disclaimer, open for questions. People that didn't have questions. Yes, you.
So Ahmed, it seems to me that you're saying, if I'm going to start solving a problem now, I go back to the requirements level and perhaps specify requirements in a different way. Is that kind of your approach to it?
Yeah. So I'm a software engineer, and to be honest, we always used to make fun of the requirements people, because people say, nobody cares about requirements. There's no time. Let's just get it done, right? Because actually, it takes a lot of time to write the code. But instead, and I keep on telling to the requirements colleagues of mine, it's like, this is your golden moment. Finally, because the thing is, once you settle on the requirements, the rest is actually easy, because the AI could shug at it. You could have a cluster doing all that stuff for you. He can bring 20 different options for you, and then you can pick and choose. But if you don't clarify the requirements, it becomes very hard. So today, a lot of the AI that has been developed is more, I would say, most like an obedient kind of servant. So I tell it, go do this, it will just go do it. So one of the things, for example, some of the research we're working on is actually having the AI said, I'm actually confused. I want to ask you back. So today, if you talk with ChatGPT and all that, they rarely, so recently they have started to add it where it actually will ask you back for clarification, but 90% of the time, it just says, okay, you want this? I'll do it. So yeah, there's a lot of work on the requirement. Requirement is very essential, actually, moving forward.
I think if there's any product managers in the room, they'd be very happy to hear that. Product managers oftentimes get frustrated by that, but it has always been, first of all, what product do you need to build and why, and how do you justify it? Then go build it.
Yes.
But,
the key thing I always tell people, there is no project that ever failed because people couldn't code fast enough.
Right.
Okay? It's just we didn't know what was needed.
Other questions?
Question about computers. So you mentioned climbing the ladder. Does the ladder move at all, or is it kind of once you're at a certain point, like a diminishing set of returns for the investments, or kind of stays where they are, or how fast is the ladder moving over time?
Excellent question. So the ladder is constantly moving. I would put it this way: to get to the top of the ladder requires significantly more effort than getting near the top rung of the ladder. So, for example, we're looking in terms of time and investment in investing a fourth of, to get into the top 20, what the top 1 system would cost. And part of that is because when you build the top supercomputer in the world, you've probably invented a new technology along with a vendor to be able to do it, to get to that next big scale goal. Getting into the bottom of the top 10 requires some money, but it's not as big a lift as going there. So why are we aiming for top 20? Top 20 supercomputer is really, really useful, but it's also a lot easier to build without teams of hundreds of people like those top systems are. And we have practicalities with regards to Queens. There are only so many of us that do supercomputing at Queens. But the ladder's constantly moving. So if you take a look at the pace of, for example, GPU compute right now, every generation, every 2 years, we can nitpick about what type of precision that we do or all of these sort of things. But let's just say in general, you're getting somewhere between a 2 to 4x performance boost every 2 years. So between what would be 3 generations or 6 years, what we would traditionally consider the life of a supercomputer, right? You've got 2 times 2 times 2 or 4 times 4 times 4 as the maximum. 4 times 4 times 4, you should just shut off your computer if that's happening. But our pace of innovation and speed ups are actually outpacing those of the 90s. So if you remember your computer going out of date in the 90s and you had to buy a computer every 2 years, It's kind of worse than that right now. And so this is why everybody's pouring so much money into infrastructure, because the economics make sense as you want to buy the latest and latest thing. Is that going to continue forever? No, not necessarily. But we've specifically designed our proposal at Queen's to be mostly industry focused with cost recovery, such that we don't have to go back to the government and ask them for money every a few years. So we can actually build a new system. They're not huge systems, but they're big computers every 2 years, so that we're capturing that technology wave, so that we're always on the forefront of, we've got some of the latest technology in-house. We won't get rid of some of our older computers because they're still useful, but we will retire them on a reasonable basis. But pretty much everybody in the community as it exists today is pretty much on a 5-year cadence, because that used to be the period in which you refreshed your computers, because every 5 years you got about the same advancement that we're getting in 2-ish years. So we have some advantages being a late entrant to the game, because we understand the new technology curve that's happening. And so we're trying to use that to our advantage to make sure that we stay ahead of the game as well. But that means significantly accelerating timetables versus what we have before. So to give you an idea, the system that we were out to over at Berkeley, I think it debuted at number 9 on the top 500, and I think it's just barely in the top 20 right now in just a couple years. So the amount of compute that's gone into that is a massive amount. If you look at just the top 2 supercomputers on that list, I believe they have 50% of the world's compute. So, and those are modern, recently deployed systems. So it's just moving so fast that it's really hard to keep up. But if you plan with a more modern understanding of where the technology trend is going, you can keep up reasonably. So that's our plan, is to keep up, but at the same time not be number 1, because we don't want to pay the cost premium to being number 1. But we're happy to build the 4th of that version of that system and piggyback on all the cost investments that were made up to that point, because that's where the cost curve comes back to.
Can you recycle any of the parts from there or no?
So that is an excellent question. So what we plan on doing with some of the older systems is first rotating them into educational use. So a 6-year-old supercomputer might not be useful right away, but it's darn useful for students to learn on, because it's pretty much the same software interfaces, it's just a little bit slower, right? So you can imagine having a top 20 scientific tool for your AI and your courses to do your applications for you for your programming classes, right? Sitting on campus. And then ultimately recycling some of those computers looks like 2 different things. There's 2 different ways to do these. Either send them out to recyclers that try to recover the minerals out of them, and there's a lot of nasty stuff in computers, so you want to try to recover that as much as you can. Or you can think about recycling them in terms of a 7-year-old or 8-year-old computer is really useful in just one part of it, like 1/60th of that system, that goes to a high school. There was a very successful program what the US did in the early 2000s, mid-2000s, where when they broke up some of their supercomputers, they distributed racks throughout Africa. There is a burgeoning HPC community, high-performance computing, supercomputing community in Africa because that happened. Because people got access to equipment that they didn't have before, they played around with it, they learn. Smart people can learn from almost anything. So we're looking at different ways that we can recycle systems that way as well. So yeah, there's 2 green elements to it: the energy that you actually use to make things and the CO2 emissions that come off of the end of it, as well as making it as green as possible when you're actually operating it. So we've looked at all these elements of different ways that we can reuse these systems. Sometimes the best option is to not pull it apart, to make sure that it finds a second or a third home further down the line. Reuse. We reuse before we recycle, right? Reduce, reuse, recycle.
There you go.
In this case, we want to reuse. Yeah.
Better term, yeah. Question in the back.
I'm just curious about the transition from R&D from university to corporate monopolies, and just the pros and cons of what's happening and your perspective on that.
Oh, I mean, there's always tons of stuff that ends up making its way out of universities and then being productized, and somebody else makes all the money off of it, right? I mean, I would say that for my own research, and I'll talk about my own research for just a second, I actively give away my research, partially because some of that research has resulted in standards. It's resulted in consortia working on things together, so we're getting essentially what we want. And from that perspective, the economic activity that came out of the university, it doesn't necessarily come immediately back to the university, but guess what? It kind of does, because those companies work with us. They bring in research funds, we do more work, we can do greater things in the future. So there's a trade-off between selling your product and giving your product away for free. Again, I kind of look at it as, patenting something versus open sourcing something. In this case, we're a university, we open source things. Karmically, that money comes around back to us in that space. But we could do a lot better job of protecting some of those initial IP generations that we have. Right? I pose the following to you. Why didn't Canada build the first LLM? Right? We have 2 major prize winners in AI. Major AI institutes were ahead of the curve on AI in terms of our talent, right? So why didn't we convert that into a product that made money? That's the first question. Part of it is because we didn't have the compute capacity to be able to do it in the first place. There's other barriers of entry to that, right? And then not just why didn't we convert it, but what can we do in the future in the space, right? So you give away your product so that people take enough of it, but then you need to have a plan of what you do when it really takes off as well, and where you go from there. So, I've had success in the past giving stuff away, but I understand that's not everybody's goal at the university. Not everything should be given away. A new pharmaceutical that cures a disease maybe shouldn't be given away to a drug company that will then charge millions of dollars per dose for it, right? The insulin should maybe not have been given away. It should have just been open source to everybody, so anybody who wanted to produce it could have produced it. Right, so there are different pros and cons to these sides. The stuff that I work in terms of system software and networks, the reason we're in so many of the large systems is because we gave things away. So I think there's a time to give things away, and there's a time to protect things and sell them, and then there's a time to actually fully give them away and purposely push them into the public domain, depending on the good that they provide. And we have a wonderful, gyms at the back of the room right now in innovations and partnerships. And he would be happy to sell you plenty of innovations from the university if you want to buy any of them, and tell you about all the stuff that we give away for free too. But yeah, there's sort of 3 buckets to go into there.
Cool. Any question in the back?
Yeah, I also have a networking question, but it's kind of out there, so bear with me. But you did a great job of describing the benefits of kind of really high, InfiniBand kind of scale communications between tens of thousands of nodes. The networking question I'm kind of thinking about, though, involves us as well. So if you figure, your voice, your fingers, your eyes, it's symbolically you're maybe dealing with 150 baud at best, like that kind of thing, right? So whether it's Neuralink or something else like that, how profound do you think it might be if there's a future coming into focus where the communication rate between the systems that are out there, or between us, once it becomes digitized, maybe just thinking it across the room in Bluetooth or whatever. This whole Q&A could have taken 2-3 seconds, with each of us having the illusion of knowing everything in Wikipedia. What would that be like? So I just wondered what your thoughts were on the rest of the network, beyond the blinking lights and actually impacting the human condition directly.
So that's a very interesting question. You're essentially talking about the network leaves, right, where we eventually extend out to. I would put to you that your brain is actually way more powerful than you think, and it's not just 150 baud. So if we quantize the power of your brain, the top supercomputer in the world is about as smart if we just put it into neurons as a dog or a cat. So and those work at about 30 megawatts. Your brain runs on roughly 30 watts. So it's a million times more efficient and essentially provides to you a infinite resolution display that you interpret at very quick speeds, right? Roughly 1/60th to 1/30th of a second, depending on how fast your brain and your eyes potentially work, right? So there's tremendous examples of where we can connect with our electronics to solve problems that we're not good at, right? So what we're not good at is recognizing what very large numbers added or multiplied together look like. We're not very good at running a ton of probabilities to tell us what we should or shouldn't do. And the links between us and this compute will let us expand our capabilities. So you can think about it as sort of supercharging or giving us super capabilities with our bodies themselves to be able to interact with lots and lots of data. But it really has to be in a form that our brain can ingest, right? So your brain's not really set up to read all of Wikipedia in 1 second, right? But your brain might be set up to retrieve a fact very, very quickly, as if it was retrieving it from its own memory. So there's some supplementary things that I think could be very interesting in the future. You're going to see augmented reality becoming much more popular rather than before you see true integration, essentially cyborgs, right, integrated together. We'll see how that goes. At the same time, everybody who wants to build augmented reality also wants to have billions of cameras all over the place and record everything that people do. So the question also becomes, I'd say this, if you could hook your brain into the supercomputer that has an AI that literally will scrape every single moment out of your brain the minute you connect to it, is that a fair connection for knowing where the nearest Chili's is immediately or knowing everything that there is on Wikipedia? So you kind of have this trade-off of what's your privacy worth, what's in your brain versus what people take out of it. I think there's some really interesting questions about that in the future. I think there's still a lot of work to be done to interface us with computers in a way that we are compatible with them. So I think we'll be working collaboratively with AIs like what Ahmed describes for much, much longer than we're actually fully integrated in with them to be able to retrieve all the information we possibly could ever want.
Right. If I could just clarify, and you're, I mean, there's the sort of human-machine interface that can be truly kind of internalized, whether it's prosthetics or anything else. I mean, there's so many opportunities. I concur that internally the communication rate is fantastically fast, given the 30 watts that we use. That's not what I meant. It's more what you just did in answering my question. So the voice out, hearing in, tapping on the keyboards. Visual field, yes, lots of data, but symbolically, if I'm reading, you know, it's slow. And you put your finger right on it. What if I'm not expecting my brain to be wired to ingest and comprehend all of Wikipedia in a few seconds? But it would be very profound to have the illusion of having memorized it, which is what this would do, along with everything else. And
Google search for the brain, right?
So anyway, that was very helpful. Thank you.
Thanks.
Question for Ahmed. What do you think it might take to get sort of everyday people to create software? Like, I mean, anyone can create a computer, theoretically, a Raspberry Pi or whatever, but I'm just curious.
To develop like software.
Yeah, like they can, but will they? Or, you know, I'm just curious, like, do developers do it now? At what point does everyone do it, or do they?
So there's part of the community, like part of the world that like to tinker, right? Okay, so these are people that do macros. They're trying to optimize their life. Okay, so today these people already can do a lot of automation themselves. Okay, like even Apple, what do you call it? Apple can let you record some macros, right? But this is very, very basic, right? Now with AI, you could build small apps for yourself. So that's not. Now the question is, you know, seniors, are they going to start coding, right? I don't think they're going to start coding, but instead you can have an AI partner that's kind of like, you know, just on your shoulder, looking at what you're doing and then kind of proposing for you. Say, okay, I see what you're doing. I think really what you want is this. Are you happy with this? And then you start the discussion at the requirement level, and then the AI can produce things for you. So there's people that are going to go and start doing it, and people that just will have to kind of monitor them and start pushing on them kind of, here's how we go about doing software development. So that would be my thought. So we have the technology to do that. Like today we can easily develop small apps interest, day-to-day productivity apps, anybody can do that today if they want to, for sure. In 2 years, it's going to be like the norm, I would say. Go ahead.
What's something that you believe about AI or about supercomputing that that you believe that you think your colleagues or other people in the industry would maybe disagree with you on?
There's no cameras.
There's literally a camera right there.
So I think right now, throughout the industry, the focus is on the idea, for example, when it comes to software development, right, is that the biggest problem in software development is actually the speed of producing code, which is actually not true at all. The biggest problem actually in software development is the requirements. That's number one. Two, once you have the code, you live with that code forever, right? This is why, if you really want to make a lot of money, you should become a COBOL developer, okay? Because most of them are dead, okay? And right now, actually, so IBM has made their own large language model. Actually, one of the main focus of the large language model was to actually be able to write COBOL code, okay? So the speed of doing something is not the goal, okay? So that's one. Second, right now, what you're seeing for these large language models is, and everybody's bragging about, oh, I can solve all these math problems, all this, all this programming. But this is what I'll call is like closed environment settings, right? So it's very good at chess, very good at Go, very good at math, very good at programming. But there's so much to the world than just this closed setups, right? There are problems, actually quite a bit of problems that are open-ended problems, okay? And once you have these open-ended problems, today a lot of these AIs are trained using what's called reinforcement learning. So it's like, you know the answer, you give it a problem and you actually know the answer, and it tries to solve it, and then you say, no, you're not right, and you kind of give it a hint, and you kind of keep pushing it. It's like training a little kid, right? But there are problems today. There's no right and wrong answer, and when you look at the your day-to-day life, there's a lot of, these problems that are very close and very clear, but there's a humongous amount that is not, right? And I think a lot of people, well, the industry goes, folks know it, okay? But the common people, when they see, oh, AI has solved this, then they start assuming it just can go all the way. So there are things that still AI will not be able to do for a very long time. Basically that, and the other thing too is you have to realize that the more you put in it, the more you'll get out. So very clear, yesterday I was talking to somebody, and for example, a lot of people say ChatGPT, has very specific words like some words that we don't use, okay? And the reason it has that is because when you talk about ChatGPT, it feels very natural, because they actually hired a lot of folks in Africa to actually say, this response looks natural to me, this one does not look natural to me, okay? These folks, the British were there 50, 60 years ago. The language that's being used is not the language that we use on a day-to-day basis, okay? But now you start becoming it's more natural and you feel it's comfortable, okay? But these people are very cheap to hire. Now, if I want this AI to replace a surgeon, I actually have to hire 1,000 surgeons, okay? And they have to actually say, this is a good decision, this is a bad decision. First, you can't even find 1,000 surgeons, and if you can find them, they cost a lot of money, okay? So there are 80% of the problems that can be solved. There are 20% of the problems that will still remain. You will still need experts. And I don't know, maybe in 50 years, 100, maybe in 50 years, we'll have more investment done at that higher level to get these problems as well automated. And that's why when I say it's not the end of programming, because the reason you hire top developers is actually for that 20% that's so hard to do.
Yeah. Right.
Okay, so can I go back to a view that I've held for more than 4 weeks? Because I have to put that disclaimer in here. So I've been a proponent for a long time that smaller amounts of compute that are still large are still very, very useful. So there's popular opinions that say, if you want to train an AI, you need 100,000 GPUs, and so you better have billions and billions of dollars. It's completely inaccessible. I've always been saying, yes, but those 100,000 GPUs are being brute forced and being used very inefficiently in the way that we were doing them, right? DeepSeek proved the world wrong in that case, right? Of the, hey, algorithmically, we can do an awful lot more than just by adding more compute to it. We can think about how we're actually doing the compute, think about it, do something more algorithmically, make a huge improvement on it. We've seen this happen over and over and over again in the supercomputing environment, and AI was just too early to see the major algorithmic improvements. I think you'll continue to see those algorithmic improvements, and with it, a democratization of the ability to use, build, and train AIs. Does everybody need to train their own foundational LLM? No. But being able to just train them and augment them, fine-tune them, augment them with extra information that you need is becoming more and more accessible and cheaper to do. So if you look at the size of systems that we've been proposing, it's in the range of thousands of GPUs, not hundreds of thousands of them. There's both practicalities in terms of we can't spend $10 billion building out a data center, but it's also that we're not going to give up just because we can't build out a super huge data center in the first place, right? And to add a second one on top of that, I think a lot of people believe that the efficiency problems with compute and AI, the fact that we use hundreds of liters of water to answer your ChatGPT request, or that we use tons and tons of energy to answer your request in the first place, is why OpenAI, $200 a month is not enough for all of the use that you use with AI. Like it can be very, very expensive. I think people think that industry is going to solve that problem. And industry can always just increase their price. Who thought that ChatGPT would cost $200 a month? Isn't that, think back 2 years. Would that be crazy for me to tell you you should sign up for this service on the internet and it's $200 a month and it's not a dating app or it's not LinkedIn Premium? Right? Like there were only a couple things that were that expensive. And pretty much everything else was cheap. It was either free because you were the product in the first place, or it was relatively inexpensive to get into, right? Amazon Prime is not that much per month. Oh, it's enticing to join up. Netflix wasn't that much per month 4 years ago. So it's enticing to sign up. So as we see improvements on that side, we have to see incentive to do it. And I always look at it and say, industry has two different paths that they can take, right? They can choose to invest a few $1 million to make their supercomputing center more green and save millions of dollars per year. Or they can spend that same time setting up 50 more racks of computer and make another $500 million. So what are they going to choose, right? And so you really have to turn to the nonprofits. You really have to turn to the public sector to help guide the efficiency improvements, because realistically, from a business perspective, it's not the business decision that you'd make. We care about it for different reasons, right? And we're still going to give those products away so that industry can be more efficient as well. I always love giving away green products and translating those into total impact of number of cars removed from the road each year. It turns out to be millions and millions of cars, and as you had more and more products, we're removing millions and millions of cars from the roadway each year. That's something that we as a public institution are more incentivized to do, and we can do that at smaller scale as well and still be relevant in the space. So I think some of those elements of industry will solve all of our problems, and then small means it's useless. One of those has been proven wrong right now. I hope that industry proves me wrong and solves all the green problems and uses no water and no energy to use their systems and figures it all out. But I think we really need to help them on number one. And then number two, with the efficiency, we still need to help there too, because we have incentive to go out and make things more efficient. So when we're in a more constrained environment, especially Canada, guess what? We rise to the occasion, we figure it out, we come up with new, revolutionary new things that we can do. And I'm hoping that we're the next place in the next few years that pushes out the newest big revolution in LLMs and AIs and DeepSeek and says, hey, we made it that much more efficient. Awesome, go Canada. And then from there, go ahead, everybody steal it, take it globally. Maybe we'll sell it, but take it and make everything more efficient. Because to me, we live on one planet. I would like to see that planet is well taken care of. So if we can make everybody take better care of the planet with almost no effort of their own, hey, that's a win for me too.
Very cool. One comment just on format. Thank you for that. We're getting the high sign at the back only because we're in a minute. We may have time for one more question, but the cooks back there, they seem to want us to show up somewhere around on time, otherwise meals will get overcooked. But I think we have time for one more question. Yeah, Hugh?
So for the supercomputer, are all nodes the same, or do you have a mix of CPUs and GPUs that you're trying to break the problem into?
The answer to that is it varies depending on the supercomputer. So some are completely homogeneous, what we call homogeneous. Every single node looks exactly the same. There are others where we split things between CPU, GPU nodes and CPU, CPU nodes. If we did that, we split them out, it's because we're fundamentally doing two different things. So if you're doing a lot of scientific discovery, or you're doing certain operations that are much better on CPUs, you could see a hospital that, for example, that would split between the two because they have different use cases that they need to combine. It's a little bit more difficult. You shouldn't change your CPU architecture. Like, you shouldn't have ARM sitting on one side of the system and x86 sitting on the other. It's just a nightmare for users. As long as you have the same instruction set, their code can generally run in both places. So the CPU code can run on the CPU nodes. Great, they're a lot cheaper to run than the GPU nodes. But most systems that we're seeing now are going to homogeneous systems, mostly just because a lot of codes have been rewritten to take advantage of both CPU and GPU, and therefore a vast majority of our jobs, our applications can do both. And so we're seeing homogeneity because it's easy, but also because it can be quite efficient. But we're still going to see in the future heterogeneity, but we're going to see some alignment in those systems as well. Between generations, though, all bets are off. You can change completely over to something brand new, and you still do well.
You have a server that distributes the tasks to different processors?
Yeah, we have system software that manages to help us chop up our task, but each server essentially is pre-assigned a portion of that data, but just by its very nature of its assigned IDs. In the overall space, you can figure out sort of, this is my chunk of work because I know the total size of the data that's available and I know what my IDs are, so I index that into an array and I find the portion of the cube that I'm working on or the portion of the matrix that I'm working on from there.
Great. Well, let's do a quick wrap up here, because the good news is these gentlemen are joining us for dinner. You have an opportunity to, and they're going to rotate around, and you get an opportunity to ping them with more questions, because I'm sure the conversation this evening has been great, and it's probably opened up a bunch of additional questions. We didn't get into ethics tonight. I know some people wanted to talk about the ethics side of this in terms of AI and supercomputing. Maybe we can have that over a dinner conversation as well. So I'm going to finish up kind of where I started. And first of all, and thank you all again for coming 2 nights and dedicating that much time, particularly given the very fierce geopolitical tensions going on between Canada and the US right now. And I'm not talking about tariffs. I'm talking about a hockey game that's going on right now that I have DVR'd and I don't want to know the answer to, right? But in all seriousness, we appreciate your time and commitment on this. And hopefully this has given you a kind of a bit of an eye-opening in terms of what's going on at the university, and again, how you guys might want to get involved with your time and participation. So on that note, if I could get a round of applause for Ahmed and Ryan, and thank you for the time.